Hope you had a nice lunch break. Now we'll have the second lecture from Professor MacDonald on Moire materials physics.
Is now correct. So the clock is now. Yeah. So, I was thinking, I got an extra 5 minutes. Yeah. No. I also have to stop according to this clock. Yeah. Okay. So this lecture is about twisted homobilars of molybdenum ditelluride. I'm going to try and give you an answer that you can hold in your hands and walk away with for why this is the only material now known to exhibit the fractional quantum anomalous Hall effect, the fractional Hall effect without a magnetic field. And so let me start with what I've illustrated here on the left-hand side, which is intended to say that the quantum Hall effect is just something that happens when you have a 2D insulator with the unusual property that the electron density at which it is insulating is magnetic field dependent. And at the end of my talk, as I said, I'm going to try to explain why a quantum Hall effect occurs, a fractional, actually a quantum Hall effect occurs in a particular system. And so what I need to explain is why is it an insulator? And why is the density at which it's insulating depend on magnetic field? So that's our goal. But first, this argument, which is connected, has been given in many different ways over the years, and is connected to the Strata formula, which is familiar to many of you. Okay, so let me start here. Imagine I have a two-dimensional insulator. I can define an orbital magnetization of an insulator. The orbital magnetization operator is up to a sign just the derivative of the Hamiltonian with respect to the magnetic field, okay? Not including Zeeman. And if you take that derivative, I won't do it, but you can see that the orbital magnetization operator is much like what you learned in classical E&M. It's the operator for current cross position integrated over the system. And that's all perfectly well defined as long as you have a finite system with an edge like in my cartoon here. And if you have a 2D insulator and you take the derivative of the orbital magnetization with respect to chemical potential somewhere inside this gap, then the current density, since it's an insulator, can't change in the bulk. It can only change at the edge. And that makes it easier to do this integral of R cross J. And you can do the integral by integrating, perpendicular to the edge at every point along the edge, and then integrating along the edge. And when you integrate perpendicular to the edge of the current density, you get an edge current. Okay? And we heard in the first lecture this morning about, microscopic theory of the 1D electron system at the edge that supports that current. But you get an edge current, and by continuity equation, in equilibrium, that edge current has to be the same everywhere along the edge. And so this orbital magnetization derivative with respect to chemical potential is just how much edge current you get change there is with chemical potential. And that's all quantum Hall effect measurement is. You put in a pair of contacts, and you have a local equilibrium on this edge, local equilibrium on this edge, and the net current will be difference between current here, and it's proportional to the difference between these local chemical potentials. Okay, and so quantum Hall effect, when it's fully developed, is really representing measuring not a transport property, but a thermodynamic property of the two-dimensional insulator. And this quantity dm d mu is, since m is derivative of Hamiltonian with respect to B, and n is derivative of Hamiltonian with respect to chemical potential, you can easily see that dm d mu, not worrying about the constants here, is the same as dn dd. So insulators that have an edge current, whose value depends on chemical potential, can only happen if the density of this system in the bulk, only if this density at which the chemical potential jump occurs depends on magnetic field. Okay? And of course, yeah. So that's what we have to explain the fractional quantum Hall effect. Why there's a chemical potential jump, and of course, this is sort of the many-body way of defining what is an insulator. It's a system with a chemical potential jump. A finite difference between the energy to add a particle and remove a particle will create an insulator. And so we have to explain why there's a chemical potential jump in molybdenum ditelluride homo bilayers and why it depends on magnetic field. Okay, so that's the objective of this lecture. So let's start with the other pre-drawn little cartoon here. If you look at these red and green things, the green dots there are supposed to represent chalcogen atoms, tellurium or selenium in our case, and the reds are metal atoms, tungsten or molybdenum. And so in this, these are group 6 elements, both tungsten and molybdenum in the periodic table. If you take a naive electron counting and take 4 electrons for filling up the p bands of these chalcogens, these are systems with two occupied d electrons per metal atom. And in the structure that these materials form, they're semiconductors actually. So there's a gap between the lowest 2d electrons and the higher 8d electrons, and which is in the neighborhood of a couple of eV or so. And the physical structure is actually going to be important for the serendipity that allows the fractional quantum anomalous Hall effect to occur. Looked at from above, the structure of these 2D systems is just like this morning. It's a honeycomb lattice, but now with metal atoms on one sublattice and chalcogen atoms on the other sublattice. And if you look at it from the side, which I'm doing here, and take a cut that goes through both sublattices, then you can see that even the individual layers in this structure, T structure, or H structure, I guess, hexagonal is the jargon, they don't have an inversion center. And that's important because it's, we're going to be, turns out we're going to be interested in states in the top of the valence band. Those are the states that are active if you just put a few holes in these semiconductors, provided that's the top of the valence band. And that is not a time reversal invariant momentum. And because we don't have inversion symmetry, you have spin orbit splitting. And in fact, it turns out that the spin orbit splitting is a half of all. It's tremendously large. The states there are split at first order in the spin orbit coupling strength. And so what happens at the Brouin zone corners is, at one corner you have some d orbital with an upspin, and at the other corner you have time reverse partner d orbital with a downspin. Okay, so no spin degeneracy in these systems, but we have the same two valleys we were talking about this morning. So I can refer to label these states in these two different valleys as either spin or valley, and I'll probably mostly call them spin, except it's kind of a funny spin because translational symmetry, because the two spins are at different momenta. Translational symmetry prevents spin flip scattering, okay? Unless, so only this order can spin flip. And yeah, so here I've drawn then this side view of two of these, of a bilayer, okay? And this structure is the metal atoms are right on top of each other, and that's what we refer to as NM stacking. So I hope from this morning you're convinced that the way to think about a Moire pattern, what happens when you get a twist, is that locally you're moving one layer relative to the other, and the important thing is the stacking. And that the stacking varies, changes by one lattice constant, making it periodic. The stacking changes by one lattice constant when the position changes by the Moire lattice constant, okay? So we want to know, say something about how this, from the second part of my lecture this morning, how the Hamiltonian of this system depends on stacking, okay? And so I'm gonna highlight two particular types of stacking. You can imagine this picture. And for example, imagine that I take the top layer and move it a little bit to the left. And eventually, if I do that, this chalcogen from the top layer will be above the metal below. So if I move, one way in stacking, that turns out to be the perpendicular direction in space, I'll eventually go from MM stacking to metal on chalcogen on metal stacking, right? So the states, it turns out, as I was sort of saying, the states at the top of the valence bands are basically d electrons on these metal atoms. So at this point, at xm, by the time we get to xm stacking, then this metal atom is sitting on, you could think of it naively as a negatively charged chalcogen ion on the layer above. And similarly, if I take the top layer and move it to the right, eventually this metal atom will be sitting on top of that chalcogen. That's what we call the metal on chalcogen stacking configuration. And so these are the three important stacking configurations to keep in mind, okay? And now I want to write the Hamiltonian of this system. So by the way, let me make a little digression. There are actually 5 transition metal dichalcogenides that form this structure, and they're all similar 2D semiconductors. Molybdenum, tungsten, sulfide selenide, and molybdenum ditelluride. Tungsten ditelluride has a different structure. So 5 of them. And so five of them. So the hetero bilayers are interesting. They're mostly actually model, they're like triangular lattice Hubbard model systems, it turns out. But we're talking about the homo bilayer, and there are 5 of them. But it turns out in these semiconductors that the hybridization between layers is much stronger at the far away in momentum space at the center of the Brouin zone. And so it can happen when you add layers, the top of the valence band goes up very quickly at the center of the Brouin zone. And in the bulk version of all these materials, the top of the valence band is actually somewhere else in momentum space. It's at the gamma point, okay? And this already happens in bilayers in 3 of the 5 cases. So these are the 2 cases out of the 5 where in a bilayer, the top of the valence band is at the K point that we were talking about this morning. So that's what makes these two materials special. And yeah, so let me say, let me write down the stacking dependent part of the Hamiltonian. So as I was saying this morning, you can think about this, specifically as the metal. So this system is described by a Hamiltonian that acts on two component spinors, because we have two layers, and if I pick a particular K, only one orbital near the Fermi level, okay? And so that means that basically we only have a layer degree of freedom. So we know that just when we look at the band structure of a single layer, right? And see that there's only one state at the top of the valence band for each stacking. And so I'm going to talk about this Moire contribution to the Hamiltonian. I hope the notation's not bad. Let me just call this H Moire. So just like this morning, it's a local, which means local on Moire scale, function of position. And so we often think of this top term in this layer spinor Hamiltonian as a potential on the top layer. But the more strict way to think about it is that it's the on-site energy for the metal orbital with the stacking at that position in space, okay? So there's potential in the top layer, there's a potential in the bottom layer, and there's hopping between layers, okay? And so, the form of the hopping is exactly what we were talking about before, except now we don't have two sublattices. The metal atoms are only sitting on one sublattice. So this is just like the sublattice diagonal terms I was talking about. So that's T of R. And it's, sum over these same three momentum boost operators. Except there's not longer any other little factors that depend on, it's not a 2x2 matrix attached to each of these momentum boost operators. It's because there's only one sublattice. And the important thing about this is I showed you this morning that the sublattice diagonal terms in the interlayer Hamiltonian vanished for Bernal stacking, right? And Bernal stacking in this case is the same as MX and XN stacking. So the important thing about this interlayer tunneling term, this local approximation, is that it vanishes at both the XN and MX positions. So at the MX and MX positions, from what I've said, that's when the two metal atoms have the most different environment. So at these two positions, MX and XN, there's no tunneling between layers, and there's a big difference in, presumably, unless there's something accidental that happens, a big difference between the metal orbital energies. at those stackings. Okay, so that means that. Okay, so that's. Let me erase this and make the next observation. Okay, so if you can imagine taking this structure and just sort of flipping the two layers around like this, what will happen is mx will turn into xm and top will turn into bottom. And so that means that, you know, if I take the top layer energy minus the bottom layer energy at the xm position, that difference in energy, I can call it the layer polarization energy, will change sign between xm and mx. And so that means that as I go through space, this Hamiltonian, you know, if this was the only term I had in the Hamiltonian, I can think that it acts on a layer pseudospin, right? And if this is the only term I had in the Hamiltonian, then at every position in space, the local spinner would align with the local pseudospin field, right? And from what I've said, that means that this two-component spinner, which we think of usually as a layer pseudospin, is at xm positions, let's say, at the north pole of a block sphere, where I choose north pole to be top layer, let's say, and at the mx at the opposite high positions, it will be at the south pole. This tunneling amplitude has a magnitude and a phase, and it turns out that this this Hamiltonian. Let me write down here the full Hamiltonian again. So the full Hamiltonian has a large intralayer momentum-dependent term, which is the k-dependence of the isolated layer in the language I was using this morning, and here it is described in effective mass approximation. Right, there's a minus sign here. I'll make this plus actually. So there's a minus sign compared to the usual kinetic energy, because this stays near the top of the valence band. So they go down when they have finite momentum. So that term I haven't written down, and then I have this term, which I can write as the average of the top and bottom layer potentials, whatever that is, plus or minus, or let's say plus delta of R, vector delta of R, dot sigma, where sigma is a Pauli operator that acts on the layer pseudospins, and delta of R you can think of as an effective magnetic field, right? So delta of R is magnitude of delta of R in some direction n. So n, the direction n, depends on position as well. So that's so this is actually, so what I've said, suggested to you, and which you can confirm, is that the direction n of this effective magnetic field that acts on the layer pseudospin, in each unit cell, it points to the North Pole, points to the South Pole, and it turns out it covers the entire sphere once. And the number of times as a function, in a 2D unit cell that it covers is a topological index of this this Hamiltonian, if you like, this potential term. And it's the same one that people talk about when they talk about skyrmions in magnetic thin film. So if you think of this layer pseudospin as like a spin, this is like a skyrmion lattice, okay? And so that's a very practical topic in magnetism these days. People want to use skyrmions to, for next generation of magnetic information technology, storage technology. But in a magnetic, a thin film of iron, you have one skyrmion for every 10 to the 4th or 10 to the 5th iron atoms or unit cells of the 2D system. Let's say it's a film. Here we have one skyrmion in every unit cell. So it's a very dense skyrmion array, if you want to think of it that way. And it's useful for some purposes. Okay. So if we're interested in if we have a small twist angle in these HOMO bilayers, that means that the Moire period is long, right? And that means that this kinetic energy term is not so important. So let's forget about this kinetic energy term for a moment and think about what is the solution of this equation as a function of position. And what it is a layer pseudospin, and that aligns with the direction of delta. We want it to be the higher of the two energies of this operator, because we're talking about holes, and we're interested in the highest energy holes. And so it would just be a spin coherent state, as people call the eigenstate of this operator is a spin in the same direction as the direction of n. I think you all know this. And sometimes called spin coherent state. And this spin coherent state would depend on parameters, position in this case. And when the spin state goes around a closed path in coordinate space, it picks up a Berry phase. And you may remember that for spin 1/2 particles, the Berry phase is S equal 1/2 spin 1/2 times the area enclosed on the sphere of directions. Okay, so that means that when you go over one unit cell, here still neglecting the kinetic energy, you cover the entire sphere once. So the integral over area in the sphere is 4 pi. So you pick up 2 pi Berry phase in every unit cell, okay? And so that's the basic property, as we'll say, that's responsible for the fractional quantum anomalous Hall effect in this system. So a very nice, serendipity, if you like, between the spatial dependence of these site diagonal terms and the spatial dependence of these site off diagonal terms in this system. So, okay. Yeah. So please interrupt me as many times as possible.
So here, assume you can easily generate bands with arbitrary integer Chern number, like C larger than 1, C equals to 2, C equals to 3. Just like you may have higher skyrmion numbers. But how to do that?
Yeah, the actual physical system has skyrmion numbers 1. So this is, as I tried to say, this is naturally emerges as the band Hamiltonian in the system. There's a Chern number, or this topological index has the value 1. And you can calculate the Chern numbers in momentum space. Probably not going to say too much about that, but there's when it's topological in real space, is mostly topological in momentum space, and the Chern numbers of the corresponding bands are 1. Some of the higher Chern numbers are bigger than 1, turns out. But there's not one-to-one correspondence between the momentum space and real space Chern numbers.
I'm just invoking that vaguely.
Yeah.
Well,
Yeah.
but most likely one can realize higher Chern bands.
Well, yeah.
Is that correct? Or
So, you know, it depends. I mean, obviously I can write down a model with higher Chern numbers, but I don't think the Hamiltonian real space Chern numbers of the Hamiltonian in molybdenum ditelluride Homer binaries will never be bigger than 1. Yeah.
You stack more layers together, you tend to get higher Chern numbers on each reaction.
That's a good suggestion. I think maybe. So that's good to think about. Yeah. Okay, anything else? Yeah.
There's one question. How precisely do you tie this delta vector?
Yeah.
On the relation to the parameters of this Hamiltonian, like this deltas in the matrix.
I think what I'm going to say next is the answer to your question, but if it's not, just speak up again. Yeah, so let me try now look about this argument that there's 2 pi Berry phase in every unit cell a little more formally. Okay, so a little more formally, I want to do a transformation, a rotation in layer pseudospin space. Which diagonalizes at every point in position, diagonalizes delta. So we can easily write down what that operator is, but we know many properties of it. And so this is a matrix, which is, delta, I'll call it plus. Do things so that the top eigenvalue is +1. So it's actually magnitude of delta minus magnitude of delta. Okay. But when we now allow ourselves to have a kinetic energy term, so this model Hamiltonian is completely local without the kinetic energy term. In that sense, maybe somewhat pathological. So we have to put the kinetic energy term in to get lots of things. And what happens when you when you let this gradient operator act on the transformation is you pick up a Berry phase. That's how the Berry phase term gets picked up. You get a Berry connection, and let's say, let me define. I can define. So the Hamiltonian is, minus p squared over 2m. When I let p act on u, I get a term like this, and let me call that the Berry connection. And so when we include the kinetic energy, the kinetic energy term, that will have some terms that are off diagonal in the representation that transform the local potential. But those will go down like, because of these derivatives operating like 1 over the Moire length squared. And so here we have delta. And let me write it like this. Okay. So make myself a little more room here. it also turns out, although it's not very important, we get a term like that, and then so this is the this is the matrix element that's locally in the representation locally aligned with the direction of n. There are coupling terms that are small when the Moire potential is long, and so we can make an approximation of an adiabatic-like approximation where the spin is locally just following the field around, and that approximation is valid when the kinetic energy at the Moire scale is small at every position compared to the magnitude of delta. And so just trust me that means twist angles less than 5 degrees or something, okay? Yeah. So we're going to make the adiabatic approximation of working with just that Hamiltonian. So this is a good point for questions. Everybody following? So this is just a more formal version of my Berry phase argument. Instead of a Berry phase, we have an effective magnetic field, and I haven't written down yet the formula for A, but E over H bar C A, as I've defined things, is N dot N over 2. That's this 2 is pseudospin a half. Okay. Oops. This is actually. So that this Berry connection vector potential I can interpret as an effective magnetic field. The curl of that effective magnetic field is proportional to the rate at which I'm sweeping out area on the surface of the Bloch sphere as I move through space. And so I can map it to a problem then that's got a position-dependent magnetic field. But the position-dependent magnetic field has the property that if I integrate it over one unit cell of this magnetic field of this 2D system, which is in the z direction, I get one flux quantum of magnetic flux. Okay? So the 2-pi Berry phase ends up getting represented as an Aronoff-Bohm phase, if you like, of this non-uniform magnetic field, and I get there's some other terms I pick up that that I don't see if I just argue about Berry phases. Okay, so I'm going to erase the board, so it's a good time for if it's not clear right now. Okay, and how much time do I have, by the way? We started at 1:30.
45.
Yeah. Okay. We're at the problem.
I'll just hit the microphone.
Pardon? Oh, I dropped mine. Is this what you're?
Yeah.
Yeah. No. Okay. Sorry about that. Okay, so I'm going to erase all that, and we're going to now talk about this problem with a position-dependent magnetic field. And I'm going to connect it to another problem with a position-dependent magnetic field, which has some Q properties, and these Q properties were noticed in a paper by Aronoff and Kasher sometime in the 1970s, and I'm just basically going to repeat their derivations. This is not the Aronoff-Kasher effect. It turns out that there are more than one paper by Aronoff and Kasher. But let me just say, so what I want to talk about is a 2D system, and maybe make it electron gas for the moment. So that means, you know, the Hamiltonian is p squared over 2n, right? In a magnetic field, I'm not going to allow the magnetic field to have any position dependence. But I'm going to say there's a spin degree of freedom, and the G factor is 2. Okay. So you may have noticed, you know, in your life that when you think about this problem, you know, if you look at the kinetic energy gets quantized in a 2D electron gas in a magnetic field, uniform field, and the minimum kinetic energy is h bar omega c over 2, right? There's a 0-point kinetic energy. But there's interesting coincidence that if you have a spin degree of freedom and the G factor is 2, then the Zeeman energy of one of the spins exactly cancels the 0-point kinetic energy. So the for 2D electron gas in a uniform field, the lowest energy Landau level has energy 0. And it turns out that that's, you know, that's doesn't really see what's special about the lowest energy Landau level, because this remains true for any position dependence of the magnetic field, okay? So that's what I'm going to show now. So let me just look at the kinetic energy Hamiltonian. So H is, you know, pi squared. Pi is kinetic momentum in a magnetic field, pi squared over 2m. So pi, vector pi is defined as minus h bar gradient plus E over C for electrons times A. Okay. So, so this is particles in a magnetic field, just like the usual Landau level problem, except that I'm not going to insist the magnetic field is uniform, but it turns out the usual approach that we take for, you know, recognizing that this turns into a harmonic oscillator problem still works. Okay, and so what we do, you know, to solve this problem, as you probably remember, is we define raising and lowering operators. So pi is pi x, pi without a subscript is pi x minus I pi y. Yeah, so it turns out, so we can check, are these still, do they still kind of look like raising and lowering operators up to some constant? So let me calculate the commutator of pi dagger, like the commutator of lowering and raising operators in a harmonic oscillator. So that's pi x, pi, I haven't, there I've defined it up there, minus I pi y. So the adjoint is pi x plus I pi y, because individual Cartesian components are Hermitian. So if I look at this operator, what does the commutator come from? It's because pi has a derivative term. Pi has, you know, it's minus I h bar dx, and, you know, px computes with py, but if the vector potential is a function of position, then I get a contribution from this commutator, dx ay minus dy ax, which is, and I forgot the E over C. Yeah. factor of 2 anywhere. I think that's correct. Look correct. Minus I. Yeah. So there's a minus I from the derivative operator, and there's an I in the definition of these. So this shouldn't be there. So this is H bar EB over C. Okay. So it's a constant. So that looks like it's not usual. Except B now is not necessarily constant. I'm allowing it to be any function of position. And so if I do that, then I get the Hamiltonian I can write as Hamiltonian is, 1 over 2m pi dagger pi. I'm going to write the pi dagger as the commutator. So I'm going to write pi dagger as commutator of pi dagger plus pi dagger pi. And so I have to put the commutator over there and H bar EB over C. Okay. Hang on, I think I dropped a factor of 2 somewhere. Somehow I think I'm supposed to have. Okay, let's not get distracted by a factor of 2. So 2. Somehow I think there's supposed to be 2 there. Yeah. So let me just put it in. So I figure out later where I dropped it, but you recognize this EB, this is B, okay, magnetic field. And the other factors are H bar over 2mc, okay? And that's the electron Bohr magnetron. And EH bar over 2mc. So this term for a G factor of 2 and spin a half is exactly calculated by the Zeeman energy. And even if B is a function of position. Okay, so there's a bunch of 0 energy states, and any state, at least any state that's annihilated by pi will remain a 0 energy state, even in the presence of a position-dependent magnetic field. So we're going to say in a moment, I'm going to talk about what are those wave functions that are annihilated by pi. And when I come back to molybdenum ditelluride, we don't have, as I said, there's no spin, right? At each valley, there's only one spin available. We don't have the Zeeman energy. And we have a position-dependent magnetic field, and we have some other terms that depend on position as well. And I'm going to make an argument later that all of those extra terms, including this 0-point kinetic energy, this part, approximately cancel. So the wave functions within, within the highest energy miniband, therefore, are similar to Landau level wave functions, or similar to the wave functions. I haven't said that yet. Ignore those words. The wave functions that are obtained that are annihilated by pi. Okay. So I'm going to erase the board again in a minute, so this is a good time for questions.
So this is an argument trying to argue that the band is more or less flat, narrow.
Yeah, so I'm going to argue that there's an approximate cancellation, and if that cancellation was exact, then the topmost, the Moire miniband that we're interested in would be perfectly flat, okay? And so, in fact, the topmost Moire miniband, I'm actually going to argue that it's flat and its wave functions are similar in the sense I'll describe to lambda levels. In fact, there's a lot of evidence that, from a theory side, that the bands are flattest when the condition I'll describe later is best satisfied. I don't know that we can make that connection experimentally yet. We can't. But that there's a wide range of twist angle over which something similar that I'll argue about later to this Aronoff-Kasher cancellation occurs.
I had
Yeah.
memory variable. Some Aronoff-Kasher paper is specifically talked about zero modes counting Dirac system.
Yeah, but it doesn't matter. So, I said non-relativistic system G equal 2, and G equal 2 is a property of the Dirac equation, right? Yeah, so, so they were specifically talking about Dirac systems, but they could have just as well said non-relativistic systems with G equal 2.
So nothing specific about dispersion. Just kind
No.
of Dirac analysis.
Yeah. Okay, thank you. Anything else? Okay, gonna erase this. And now we're just gonna consider what are the states that are annihilated by pi, okay? So that's where we're going. And maybe I'll keep that up there anyway. Okay, so we want to find those wave functions for which when pi acts on it, you get 0, okay? And in pi, you have this, the vector potential term, but you also have px minus I py. And so what I'm going to say now depends on the fact that, that this is minus I h bar dx minus I dy. That's the canonical momentum contributions, and then plus E over C ax minus I ay. So this in pi, the derivatives with respect to x and y appear only in this combination. That's the thing we're going to exploit. So we're going to change variables from x and y to z, which is x plus iy, and z bar, let me call it, or which is x minus iy. And you could easily show that that dx minus I dy is minus I h bar d times 2, actually. 2 times d z bar plus E over C ax minus I ay. Sorry, that's wrong. dz. Okay. So that's just changing variables from x and y to z and z star. And so the operator pi only has derivatives with respect to z. Doesn't have any derivatives with respect to z star. And so that suggests that we look in trying to define, we look for states, wave functions annihilated by pi, which have a form that exploits this property. And so let's look at this wave function as, let me write it as e to the minus some unknown function phi, okay, times a function that's independent of z, depends only on z bar. That making sense? And so if I do that, then I let dz act on this function. Phi might depend on z. So I get, dz brings a factor down from this, but dz has no effect on f because f doesn't depend on z. And so I get, so what I need, a function of this form will be annihilated by pi, provided that minus 2i h bar dz phi plus e over c ax minus I ay equals 0. Okay. So any function phi that satisfies that will give us a solution. So we can make this simple by taking another derivative. Let me actually, minus 2i h bar. I'm going to take another derivative of both sides of this equation with respect to z bar. And part of the motivation for doing that is dz bar times dz is just the way you write the Laplacian operator in terms of these complex coordinates. Okay. So we need to know what is this dz bar of ax minus I ay. And so that's equal to, if I just take this term over here, do a little side calculation. Dz bar is, so that's e over 2c, just like up here, dx plus I dy of ax minus I ay. Okay? And so what is that? That's e over 2c, divergence of A, which we can choose to be 0. And magnetic field, dx of ay. Okay. So the function phi then is a function where the end of this, these cancel. Sorry, the factors of I cancel, and what you get is dz bar dz phi has to equal minus 1/4. There's a half here, and there's a half here if I take it to the other side. And then I have h bar c over ed. And b is a function of position, okay? So any function, any phi of that form, multiplied by a function of z bar only, is going to be annihilated by pi. And in the case of electron gas with a G factor of 2, is going to have 0 energy. And now it feels like I want to do this. but not available. Okay. This may be familiar. In the case of a uniform magnetic field, the wave functions are of the form of, let's say, powers of z, z bar, as I've written it, times magnitude of z squared divided by this thing, which is 1/4 magnetic length squared. So you can easily get the uniform magnetic field lowest Landau level wave functions. You can read off this already. And yeah, the next thing is bad whiteboard management here. I hate whiteboards, but let me. I don't want to erase that, so I'm going to make my next remark down at the bottom here. So if it's too hard to see down at the bottom, just let me know and I'll have to erase. Okay, but what I want to say is something about how big is this space of wave functions that satisfy this property. And the way I'm going to do it is I'm going to say consider consider squares of wave functions for f of z just being a power of z bar. And so psi squared I'm going to consider to be just e to the minus u. So then I can think of this as some classical statistical mechanics problem. And this is what people, plasma, sometimes refer to following. Bob Laughlin's work on fractional quantum Hall effect as a plasma analogy. Okay, it's not the only way to say this, but if I interpret a wave function of this form squared, then what is u? U is 2 phi minus, and if I take, this is for the case where f of z bar is z bar to the n, okay, minus 2n log z. And
Not DC bar.
yeah, so absolute value doesn't matter, right? Yeah. So this is the repulsive interaction of, let's say, a test charge. With, this log z is the Fourier transform of what people sometimes call the 2D Coulomb interaction. The 2D Fourier transform of, the way I'm using it here, of 4 pi over q squared. The thing that has, Laplacian of potential is charge density. The interaction with a point is twice log z. Okay, so this is so this is I'm just wondering about the factors of 2 here, but this is the classical one-body potential of for 2D Coulomb interactions, where there's a point charge at the origin and has a repulsive interaction, and and there's what you can think of as a background potential, and charge density of that background potential, Laplacian of phi, Laplacian of 2 phi actually, is equal to up to constants the magnetic field dependent density. Okay? And so let me not try, since time is running, to get all the constants right. You can go back and do that yourself. But the condition, so let's imagine I have a finite size system with a position dependent magnetic field, and outside some radius, the magnetic field goes to 0. Okay, this background charge density goes to 0, and the condition for this wave function being finite at infinity, not blowing up at infinity, being normalizable, is that that n has to be smaller than the total background charge, which we put in the constants properly is the total number of flux quanta enclosed by the magnetic field. So this means in order to be normalizable, the number of normalizable states is 1 state per flux quantum. Okay, and there's 1 flux quantum we said per unit cell. So for we're applying this as an approximation to the original Moire band. And so what this says is the number of states in that band is equal to the number of unit cells in the system, which is, we know, a property of block bands. So this is kind of a reality check in our system, right? On this calculation. And okay, any questions? Because now I'm going to erase the board. Okay, so there's only one more thing I want to say. So I promised at the beginning that I would give you a reason that you can hold in your hands for why molybdenum ditelluride has a fractional quantum anomalous Hall effect. Okay, so so I'm going to assert that there is a something analogous to the cancellation of 0-point kinetic energy and Zeeman energy. And the way that happens actually is that there are 2 terms. It's a race now, but there's 2 terms in the 2 terms in the effective Hamiltonian that are large. And the 2 largest ones are the 0-point kinetic energy, which is a function of position. We usually draw this, Moire unit cell for the in real space, so that at the center of the cell you put the MM stacking, and out on the zone boundary you have alternating MX and XM stacking, and that's the normal coordinate system we use. And both of these terms I mentioned to you tend to be largest out near the zone boundary. And they're also opposite in sign outside the zone boundary. You're going to ask me about this later. And so it turns out if you sort of integrate around the zone, I shouldn't have said zone boundary, around the Moire cell in real space, around the boundary, a region in the boundary where most of the contributions are coming from, you get something that's small, near 0. Okay, you can tune it to optimal, like I was saying before. And so part of the argument is, out on the zone boundary, it turns out the positions where the kinetic energy 0 point kinetic energy is big, and the potential terms are big. They're not the same, but the magnetic field tends to be large between xn and nx positions, whereas the potential terms tends to be largest at the xn and nx positions. The argument is that the wave functions in the lowest Landau level, since they have the lowest kinetic energy, are smooth wave functions, and they don't see that rapid variation in space. Okay, and there's numerical calculations you can do to back up that assertion. So let's just accept for the last minute that there is something that's analogous to the cancellation between 0 point kinetic energy and the Zeeman energy in the Moire problem. Now I'll come to the last thing. So I want to explain why there's a gap at a fractional filling, and why the density at which that gap appears depends on magnetic field. And so I'm going to use that the number of states in this Hilbert space, which is, let me call it M max. So the powers of Z bar that I'm allowed to have go from 0 up to some maximum value, which in the absence of a magnetic field is the number of unit cells. But now I want to say it's the number of unit cells plus the number of flux quanta. That's the number of states in this low energy Hilbert space if I add a magnetic field. And again, that's a reality check for this picture, because we know that this is the Chern band, and for every flux quantum I add externally, the number of states in the Chern band will increase by 1. Okay, so that is the one way of understanding the integer quantum anomalous Hall effect. And the fractional quantum Hall effect that we can discover, by just using Bob Laughlin's argument and saying that in this Hilbert space, why does the chemical potential jump? And we can say the chemical potential jumps because there's a class of low energy wave functions where the wave function vanishes more rapidly when the particles get close together. This class of low energy wave functions has that the wave function vanishes like the third power as any two particles approach each other. Since this analytic part of this wave function, and I've changed Z bar to Z here, but it doesn't matter. Since this is now many body wave function, and first quantization, and if the wave function vanishes like the third power when any two coordinates approach each other, that means I can factorize that out of the wave function. And so the true wave, this class of wave functions has vanished as cube, and then there's a whole bunch of these wave functions in general, because I can multiply this by any symmetric polynomial. And then I have, this convergence factor, if you like, that's associated with the magnet, how many flux quanta are in the system. And so, so the answer then to the, let me draw this again. Yeah, so we're talking about low energy, low interaction energy states, and so the idea is that as long as I can make a many-body wave function that's like this, then the chemical potential, the energy to add an extra electron, is small. It's small because I can add an extra electron without having to put it, very close, like making the wave function vanish like the first power. And then when I reach a certain density, which we'll calculate in a moment, I can't do that anymore. So n star, the place where the chemical potential jumps, is the maximum density where I can live in this Hilbert space. Okay? And so in order to calculate whether this wave function, many-body wave function in this Hilbert space, I can take any one of the coordinates, let's say z1, and calculate the power to which it appears. And z1 has a whole bunch of difference coordinates, z1 minus z2, z1 minus z3, all cubed. So those factors, m1 will appear to the power of 3n, okay, up to some correction. And I want to make sure that m1 is less than or equal to the number of the maximum value that's allowed right here, right? And so if I want to, I'm just interested in the maximum of n at any given density, I would just choose q equal 1. So that's the maximum of n, and it has to be less than or equal to the number of unit cells plus, if there's a magnetic field, the number of flux quanta plus from the external field. And so that says, that there's a jump in chemical potential if I divide the right-hand side here by 3n, that means that that the band filling factor at B equals 0, at which there's a chemical potential jump, is a third. And then if I add more flux quantum, then the density at which that jump occurs will go to a higher density. Okay, it's 1/3 filling of the band degeneracy in the field. Okay, which is I'm not sure if I called it this when I was there, but that's the Schrader formula. The fact that the Hall conductivity is related to the field dependence of the density at which the state occurs. Okay, so I think I've used my time. I should stop, but I will entertain questions, and I'll stand here as long as anybody's interested in chatting.
You mentioned that the real space topological index and the k-space topological index generally coincide in these systems. Is that related somehow to the position momentum duality you get the lambda level problem, or is the argument different?
Yeah, so they don't coincide.
Don't
coincide quantitatively, but they do coincide qualitatively. For example, as you may know, one of the valuable experimental tuning knobs in these systems is the displacement field, the potential difference between layers. And so you add a displacement field, it will tend to polarize the electrons in one layer, and you lose the topological structure in real space, and you also lose it in momentum space, but not exactly at the same point. Interesting.
Thanks again for the talk. Can you explain again, at least in the TMD context,
yeah,
where does the G equals to 2 come from? which is important to cancellation and get the zero modes, approximate zero modes of that.
Yeah, so let me try it again. This is maybe where PowerPoint version of this talk would be better. But yeah. So this is, I'm drawing a real space picture of one unit cell of the Moire material. And usually we do this, as I was saying, with the center, with the origin defined as MN stacking. And if I do that, then it turns out MX and XM stacking alternate at the corners of this Wigner side cell. Okay. So the effective, the terms that we want to cancel, and that certainly do not cancel locally. So the most important terms that cancel are H bar, 0 point kinetic energy. And I guess the way I've defined things, that's with a minus sign, right? And so that's the effective magnetic field. And I said this effective magnetic field is proportional to the topological index density in the adiabatic approximation. And here, when I go around the boundary of the Brouin zone, I'm going like North Pole, South Pole, North Pole, South Pole. And when I go from North Pole to South Pole, turns out that the tunneling between layers vanishes at these points, as I mentioned. But in between, it's non-zero, and it stays varies transversely here. Okay, so if you do a calculation, that has a, now I got the tops mixed up here. Let's see if it works. Okay, now I got them right. Okay. Turns out the magnetic field, this non-uniform effective magnetic field is peaked at these positions. The other most important term, all of these terms that appear that you want to cancel, we call in language that was invented by one of my former students, Jingjian Shi, who's at Argonne now. He called all of these terms that would vanish if this story was perfectly exact, the residual terms. Okay, so I'm writing down contribution to residual terms. The next most important contribution to the residual term is this potential term, right? The difference in potential between the top layer and the bottom layer. Qualitatively, the average potential in the two layers doesn't vary so much in position. And this is maximum. It's positive, and it's maximum at these positions. Okay, and so let me. So here's the function, roughly speaking, that we want to cancel. And what I was saying is that if I, for example, took this residual potential and I Fourier expanded, as you know by now, I want to do, right? So it's a way of simplifying these problems to truncate the Fourier expansions. And so what Fourier coefficients describe this variation at the boundary of the cell? The first shell of reciprocal lattice vectors basically sort of measure what's the difference between the inside and the boundary. So this is some higher shell of reciprocal lattice vectors. The average of these two contributions, they cancel on average to a good approximation, but they don't cancel locally. And this spatial variation is between red and blue, green and red, sorry, is very fast on the Moire scale. The size of the entire structure I draw is the Moire scale. And the argument is that, supported by numerics, is that the wave function in the lowest kinetic energy band is smooth, and it just averages those out.
Right, and after that we have to stop here because of the time constraint. So let's thank our speaker again. Take a short break.